some of you know it a little bit, and I will show you what it is. So basically, we have a pointer. Yeah. Okay, so the cerebellum, as you may know, is the small brain back of the brain. And this is so important.
Is this one cerebellum?
Here this one takes quite a bit of the brain. Here you see a cut. It's very and so of course the first question we can ask is why will I speak about it? So this is a region, this is a major actor, as I will try to remind you, in motor coordination and in learning precise movement.
Vincent, can you speak louder or have it closer to your mouth?
Okay.
Yeah.
So it has a structure that is very ordered. So can you hear? Yes. So it's a structure that is much more ordered than other neural areas. It's a very crystalline area, I will show you. And of course, the fact that it's crystalline helps to make sense of the different cell type and connectivity. I will show you how this is going on. And so for this reason, since it's ordered and we know the connectivity basically, it has attracted the attention of many theoreticians and experimentalists, say, in the last 50 years. And actually, this was used to develop many of the ideas in computational neuroscience, including those that Nitya reminded us about today. So this will be the lecture, maybe not in full, but because now time is a bit running. And so I'll try to today to remind you of things that are rather classical and recent experiments. And then, of course, although it's in some sense much simpler than other parts of the brain, there are many things that are poorly understood. And for example, it's not really understood how a brain in this area learns, because we have algorithms that are not very biologically relevant. And so this is the question Nitya described, and I the lecture on Sunday, I try to explain the current idea about it. Okay. And of course, you are welcome to enter anytime. So what I was planning to cover today, and I think I probably won't have time to do that, is first to explain you some experiments, some very classical experiments that show what's the role of the cerebellum motor movement, try to remind you what is the cerebellar anatomy. I said it's very crystalline, but at least it should be described. And then, okay, so there is a very influential theory that dates back to David Marr, which at the time was interpreting anatomical results by Eckers, Ito, and so this was a very influential theory, and that is up to this day used to interpret experiments, although it has been modified in some ways. And so this led to different concepts. One is that it is useful when you have data to map in a higher dimensional space. And this is, as you will see, because data is mapped to a layer that is called the granule cell layer. And these cells are actually the most numerous in the brain. They make about half of the number of neurons in the whole brain. So that's that's one idea. So that's mapping in high dimension. This is realized here. The second idea is again very related to what Mika told us, is that the central set of this structure acts as perceptron, so basically as linear decoder with a fretboard. Okay. And then, okay, if I have time, I show you that, okay, if you want to do timing movement, you need to create a basis function for acting at the right time and how people think it is done in the cerebellum. And okay, maybe then we conclude with putting it all together. Okay, some experiment. So the first experiment is very simple. If you turn your head, or if somebody turns your head, your eye will go in the other direction. So this is called the vestibulo-ocular reflex. So your eye will turn just to maintain your gaze on the target. Okay, so that's a simple experiment that is done here sketchily on the monkey. If the head turns, the monkey always see a single banana. But now if you put magnifying glasses, if you do the same experiment, then when you turn the head, the glasses are tied to the head and they magnify, so the image on the retina moves more than it should without glasses. And so what you see is that the image, or what the monkey sees in this experiment, is that the banana sleeps on the retina. And so what the monkey learns to do is to adjust, instead of just compensating for the turn, it just turns more the eye or less depending on what. So for the, in this case, when you turn. And so that's the what happened when you put the goggle at first. But then, in the course of a few hours, you adapt, and then you see again a single banana. So this is what is sketched here. You have the head. In the normal condition, the eye goes in the other direction. There is no sleep on the retina. If you put magnifying glasses, you have the head. The eye turns as they do here, because nothing has adapted, and you sleep on the retina, the image sleep on the retina. So when things, you adapt, the eye turns more, and then you maintain this image on the retina. So this is the adaptation of the vestibular-ocular reflex. And people have shown in the course of years that this is really dependent on the cerebellum. You can plug the output of the cerebellum, and you won't adapt. You can do all kinds of manipulation that are really cerebellar specific, and you will plug this reflex. So now, of course, in modern days, this has also been done in mouse. So the way people do it, so the way people do it in mouse is just to put the mouse on the turntable, and then you can turn the mouse, and you can turn the visual field. So either you don't turn the visual field, and this is the visual situation, or you turn it together with the mouse, so then nothing is turning for the mouse. And you can turn it more, etc. So you can change the gain of this reflex in both directions, depending on what you do with the visual field and the purpose. And this is a way to investigate what is going on more easily than in the moment. So that's one of the classical experiments. Okay, the other very classical experiment is just classical conditioning. So it's called, here it's hybrid conditioning. So I put it in a modern setting. So you have air puff. So if you have an air puff on your eyes, you tend to close the eyelid because it's not very nice. Okay? So that's the unconditioned stimulus, if you put an airport, you close your eyelid. So now you can try to pair it, like in the classical Pavlov's thing, with the light. So before putting the airport, you can switch on the LED, for instance, in this experiment. So this LED will be here. And then you do the experiment where you pair first LED and then the puff. And after a while, this mouse or any animal will close its eyelid in anticipation of the air puff. Just so you see before, there was the air puff and then the eyelid. So this is the eyelid movement, traction of eyelid closed. Okay, so here you close the eyelid after the puff. But now if you have this conditioned stimulus, you will almost close the eyelid before the puff. So this makes sense. You don't want to receive the air puff, you close your eye before. Okay? And again, so if you change this time, you close your eyelid just before the air puff. Basically, the time when you do that is tied to the puff, not to the LED. Okay? So in some sense, you have an adaptive time scale here. You have the LED and you know that you should close your eyelid certain time after. Okay? So in some sense, the cerebellum, because this is again linked to cerebellum, and to have shown it, the cerebellum should not only modify, trigger this eyelid, but compute the time in some sense. Right? Okay, so these are simple tasks. And now, of course, the cerebellum is thought to be involved in coordination of movement. So what I was showing you are very simple movements, like closing the eyelid or moving the eye. So there are few muscles that are there, but of course, in more complex movement, you have very many muscles that are involved, and so you want to understand this. So I show you a movie, if it works, from Megan Carey's lab at Champagnat. So that's a normal mouse. That actually the movie slowed down a lot, as you see. It was slowed down more than 10 times, so actually at least this mouse is running here. But you see that it's very coordinated, this movement. We'll do again. So here you see that what the mouse is doing is putting these two, the front and the back at the same time. And she alternates very nice. And this, if you look at the tail, it's quite straight. It's a nice movement. Okay, so now we can look at the cerebellar mutant. The movement has repeated too much. Okay, so you see now that, okay, here you see that every bow is put at a different time. The tail is waving in all kind of fashion. So in some sense, you have the mouse has lost, because this is a Purkinje cell degeneration. I will show you the anatomy. This is the central cell of the cerebellum and the one that is with the single output. So in this mutant, you have this kind of very coordinated movement. Okay? And so this is, and of course this, just as a technological aside, this is this poseless marker that is now used all over the world in different labs. So this is a technology that is deep marker. Okay, so that's a simple thing. Oops. Okay, so this, of course, I just show you that it can be quantified. And so, actually, there are things that are nice in this quantification. If you look simply at the speed of the mutant, it's actually smaller than the speed of the wild type, as you can see here. But actually, this is not really a defect of the, it's not really a defect of coordination, or it is just that this mouse, for some other reason, are smaller, okay, these mutants. And so if you compare with mouse of the same size, they are normal. So in this respect, the speed is not affected. What is affected? So you see here, they match to control to animals that are smaller than normal animals that are smaller. What is very different is what you saw is that, okay, the excursion, maybe we don't so it, but the excursion of the movement in the wild type, that is the black line, is kind of straight, it stays in X and Y coordinates. It's rather straight. Here you have big excursion, and also in the Z direction, the mutant is much more useful than the okay, so there are all kinds of, as you saw in the movie of different things. Okay, so in the same lab, I show you more, maybe more interesting or more cruel experiment for the mouse. So here what they try to do is to have the mouse walking on a split bend. So here, if you look at this, the mouse is running in this corridor, so there is a plexiglass corridor, there are two motors, so you are trying to move on the belt where the two half of the belt are not moving at the same speed. So that's a classical experiment also in human, and as you imagine, you adapt this thing. At first, it's very disturbing to move on this split belt, but you adapt. So you can do that in mouse, and so this has been done here by Megan Carey and my collaborator. And so what you see is that the stride length, so stride is the size of the step, the size of this, you measure it from lifting to touchdown, so that does not adapt. And so what you do is you make a bigger stride on the fast than on the slow. But this is, you jump first and then you don't adapt on the course of experiment. But what you adapt is where you put your feet. So here, if you look at the difference, so this is the step line, this interlinked thing is the, it's not so easy with the microphone. So you have one toe on the ground, you put the other one and you measure the distance between the two. Okay, so that's the step length. And this adapts in the course of the experiment. Okay? So it starts big, and so basically at the beginning of the experiment, you put the feet, the foot on the slow belt to in front, and then you adapt. Okay, so that's the adaptation. And so in this lab, they could show that this is cerebellum dependent. Again, if you have the same mutant that I showed, you don't have this adaptation. And now you can put, you can have a chemogenetic approach and try to inhibit different parts of the cerebellum. And you can locate precisely, not so precisely, at least the area where this is taking place. So this is what is done here. What you put this inhibitory blockages. So that's basically the controlled experiment. And also one motivation is that the cerebellum is also implicated not only in motor movement, but basically in different cognitive tasks that necessitates time evaluation or coordination. So cerebellar patients are, of course, impaired in motor movement. For example, they cannot, when they try to reach a task, here, when you do that, you have everything that is moving at the same time. In cerebellar patients, you would have like this and this, so movement at succession for different muscles. But so, apart from movement, you have time evaluation deficit in a cerebellar patient. So this was shown long time ago. So for example, if you have to judge the timing of two sounds, this is there. You have also activation. So in many experiments use in human for cognitive tasks, we use fMRI or PET. So if you try to do word association tasks, like if you show a word and you have to produce a verb that is commensurate with this word, like show cake, and you have to output something like eat or tree, and you have to output climb, then you see a big activation of the cerebellum. And of course, if you have to output the word, the motor action in fMRI, you subtract the motor part just by having people pronounce this verb before subtracting this. There are also cerebellar implication in different psychiatric dysfunction, like autism or schizophrenia. And you have also now many recent tracing studies that show a loop between the cerebellum and the cortex via the thalamus. So there are no direct link between the cortex and the cerebellum, but you have many disynaptic loops. Okay? And so it was proposed. It was proposed many years ago that maybe the cerebellum, which plays a role in movement coordination, that's well documented, maybe plays a role also in some kind of coordination of different thought modules, but this is very speculative. Okay, so now that I've shown you and basically some tasks that the cerebellum does, I'd like to enter a bit into how this structure is formed. It looks like. So I try to show you the cerebellar anatomy. So this is a small region of the cerebellum that has been cut. And here is sketch. This is taken from this classic textbook. So what you see here, so you have this very these principal cells that are actually very ordered. So you see this is a very, very regular lattice. So that's what this has attracted attention. And what is nice about the cerebellum is that there is a single output. So all the output is coming from the axon of this principal 13 cell. So there is a single output that targets nucleus that are called the deep cerebellar nucleus. So there is a structure here that is targeted by the cerebellum. And then there are only two inputs, two kinds of inputs. So one is gives information about sensory input, sensory information, or the proprioceptive information through this mossy fiber that target this very numerous cell population that are granule cells. And the other very striking input is coming from the structure that's called inferior bodies. And here, as we see in the next slide, each cell in this structure sends an axon, and this axon will target a few Purkinje cells in a very special manner. So each Purkinje cell will receive only one input from a single cell in this structure, and I will show you how it looks. Okay, so I show you first this central cell of the cerebellum. So there is the soma, and here is very big. So this is a 250 micron by 250 micron, so it's a huge cell. It's, as you have seen on the previous slide, it's very planar. And so on here, as we see in the next slide, on this huge dendritic tree, you have about 200,000 synapses from the perpendicular axon that are called parallel fibers. So I will show you that. So this is a very big tree, dendritic tree, that receives an enormous amount of information from this transverse axon, and this is used to limit action potential at this point. So I'll show you that. Okay, so here I show you a little bit more of this. So here you have this Purkinje cell, and you have this parallel fiber. So these parallel fiber are the axon of this granule cell. So remember, these granule cells are this very numerous layer that receive all these inputs from the body, like sensory and proprioceptive input. So here you have this. So these are all fibers that convey this input. Then this is targeted to this granule cell, and basically each granule cell takes input from 4 fibers. You see that we have this very simple structure where you have the soma and 4 dendrites, and they just take input on average from 4, so it varies from 1 to 7, and the majority is around 4 and 5. And then it goes there, and so here you have all these axons, and this, so you have all the Purkinje cells that are like here, and these axons traverse the dendritic structure, and here you have, as I was saying, a lot of synapses on this Purkinje cell. Okay? So that's the input, so you have information about what is going on in your body. It's targeted by the granule cell, it's conveyed to the Purkinje cell, and then the Purkinje cell sends, in some way, process this input and send it back to the deep cerebellum. And here I show you the other input. So this is this tiny fiber that is wrapping around the Purkinje cell. So each Purkinje cell receives one tiny fiber that wraps around. Okay? So I know it's a lot of information, but just to have the structure. So this, you have the information that is here. The body is transformed at this granule cell layer, conveyed to the Purkinje cell, which does something with it and emit it back. And there is an input on this Purkinje cell coming from this tiny fiber. Okay. So I'll show in the next slide a small diagram of that. Okay, so here is the granule cell, the parallel fiber, the Purkinje cell, and you see that, okay, it received this information from this tiny fiber that is wrapping around. Okay. And then it sent it back to the deep cerebellum. So one particularity of the cerebellum is that the input here, the mossy fiber, and the climbing fiber excitatory, and the rest of the structure is only made of inhibitory neurons. So the Purkinje cell is inhibitory, it inhibits the deep cerebellum. Okay? So everything inside this, you have some here. You have also interneurons here that will describe the later. So you have this parallel fiber is also targeting interneurons that are the Golgi cells that feedback on the input. It's kind of negative feedback on the input. And here you have also the basket and okay, so sorry. So did you hear me in the back? Okay. Okay, so that's basically the sorry. Okay, so that's basically the anatomy. So again, so each Purkinje cell receives a very strong input from the timing fiber and very many small inputs from this parallel fiber. We have the cell and here the deep cerebellum. So that was anatomy. So now if you look, if you record from Purkinje cell, the fact that you have these two different kind of inputs is reflected in the kind of action potential that the cell emits. So when it's stimulated by all these parallel fiber, it emits a sharp spike that's called a sickle spike. So that you see here in this recording. This is from I took a random one from Javier Medina's lab. And so if you have input from the timing fiber, you have a huge different form of spike, a much fatter spike that's called a complex spike, and that you can recognize in extracellular recording like here. So you have in each Purkinje cell, so this central cell of the cerebellum, you have two kinds of spikes, the simple spike and the complex spike, and you can recognize them when you do electrophysiological recording. Of course, you're welcome to ask a question at any time. Okay, so just to conclude this very short summary of the anatomy of the cerebellum. First of all, you see this is something that goes back quite in time. You see a beautiful drawing by Harmony Carral as many part of the brain, but here you see again the Purkinje cell, the granule cell, the parallel fibers, and you see that Carral was very describe everything in great detail, so you can see here that most of them are 4 or 5, but then you have some of them that are a bit more in this granule cell. Okay? So what are the numbers here? So the number of mossy fibers is about, so this is the input. So you have about 2 to the 5, 10 to the 8. Okay, so that's a lot of input. But then they go into this granule cell layer, and you see that, okay, the number of input here that you have is amplified, is put in a much higher number of granule cells. So here, basically you amplify this by more than 2 orders, 2 orders in magnitude. So, and this the granule cell I was saying are very numerous, and they are more than half of the total number of neurons in your brain. So each of them connect to 4 or 5 fibers. And then, okay, so you have this huge number, and then it's transformed on a much smaller number, so it's very compressed by the Purkinje cell. So there is a huge compression here, and this is done because you have each Purkinje cell is processing a very high number of these expanded inputs. Okay? So you have a large divergence from mossy fiber to granule cell and a large set of granule cell inputs on each protein. So you see that you have all these kind of facts. And so this, of course, has inspired people to try and make sense of why you have this structure, what could be the purpose of this design.
There's a question.
Yes? Nice.
I'm sorry, could you please specify, so granule cells are the most likely facilitator in Purkinje cell, climbing cell can inhibit anything at any time, and most fibers are responsible for the general.
So maybe I'll go back to, I will try to explain you the view that has been developed over the years, so this will
Yeah, and maybe I also have an additional question, because like usually when you read about the cerebellum, there are also other types of cells. For example, Golgi cell, right?
So let's go back.
Usually they are yeah, so there are also other types of cells. For example, Golgi cell, as far as I remember.
Yeah.
And in books, they are usually just skipped. There are a few words about them, and that's all. Why so?
So I want to be fast. I will try to tell you what's the idea about all these kind of cells. So as I said, I mean, so there are not so numerous other cells. I mean, there is the Golgi cell, as you said. So the Golgi cell is making a feedback on the granule cell. So this is inhibitory on the granule cells. Okay, so this is here. And the other type of cells are this. So this is a 3-layer cortex. So one layer is a granule cell layer. You have the Purkinje cell layer. And here what is called the molecular layer. This molecular layer. Yeah. So in the molecular layer, you have the parallel fiber, but you have also these inhibitory interneurons that are stimulated by the parallel fiber and that inhibit the Purkinje cell. So that's the three types of cell that you have.
Yes.
And as in some region of the cerebellum, you have also, as we will see, another type of cell, but this is what is happening in most of the cells. Okay? And I try to tell you what people think about all these cells.
Can I ask a question?
Sure.
So we have two, the most fibers and the one from the inferior, right?
Yes.
So these two inputs have direct projections to the deep cerebellum nuclei.
Yes.
But also like they bifurcate to go to the cerebellum, Purkinje cells, right?
So which one?
Like
So here the climbing fiber is wrapping around the Purkinje cells.
right, but
And it has also collateral to the deep cerebellum.
yeah. So my question, what is the are those collaterals kind of what's the function of those collaterals?
Okay, before we go to the function of this collateral, it's better to try and understand everything, no?
Yeah.
Because at the moment we don't know even what's the function of everything.
Okay.
No? I mean, you have the structure, I described it to you, but we don't know the function. So I try to tell you a little bit what people think about the whole thing, and then we can go into more detail, think what could be the role of this. Okay? So just maybe to your point, because it's interesting. So in some sense, the whole cerebellum is so the deep cerebellum nucleus are given, so they have a direct input. So like here maybe, So yes, you have the percerebral nucleus, you have the deep cerebral nucleus, you have the descending motor system, and the whole structure is actually making a side loop and targeting this deep cerebral nucleus. So what the whole structure is supposed to do is somehow to correct the input from this deep cerebral nucleus. Okay, so basically, the ODIV is given some information. But to understand maybe this, it may be good to try to see what's the idea of what the ODIV is doing. So the ODIV actually, so these cells are emitting action potential at a very low rate every time, all time, 1 Hertz, basically stochastically. And from time to time, they give a coordinated discharge. So we'll see what this is. Okay. Okay, I don't know. Sorry. Okay, so exactly to answer your question, I try to tell you what people have thought about that. So, okay, so the first, so the granule cell, the idea, as many of you have probably thought of, is that to give a sparse representation. So basically these ideas go back to David Marr, James Albus, and Ito, who actually did experiment to verify some of them. So the idea here, okay, one that is rather obvious is that the granule cells are expanding the information in a higher dimensional space. Okay, so that's the idea. So the Golgi cell, so somebody asked about the Golgi cell. So the idea is that the Golgi cell, since they fit back on the input, they are in some sense enforcing the sparse fraction of active granule cell. Okay, so if you have too much, you have a negative feedback, so you enforce a negative. That's the idea, at least. And so now the idea is that, okay, this synapse between parallel fiber and the Purkinje cell is the main plastic site in the cerebellum. Okay? And so the idea is that what the tandem fiber is doing, since it's wrapping, so each Purkinje cell receives input from a single tandem fiber. The idea that has been developed is that the plasticity at the central synapse is actually controlled in some sense by input coming from the inferior olive. Okay, so the idea is, so that was, so at the beginning, what Marr proposed is that, okay, here you have the tandem fiber, so the idea of Marr was the tandem fiber was driving the Purkinje cell to phi, and in the course of time this was replaced by molecular, by firing due to input to this parallel fiber. So in some sense this made quite a lot of sense, but it requires that these inputs are potentiated in some sense. And actually, in reality, they are depressed by the when the tandem fiber emit the spike. So Albus anticipated that for other reasons of stability and proposed that what is happening here is that the tandem fiber is actually sending an error signal. So like as we saw in the say in the VOR, when you have sleep on the retina, you have an error. Clearly, for the eye, it's an error, so you will have fiber that emit spike and that say to this Purkinje cell, this movement is not correct. And the idea is that in the course of time, we will check this synapse and correct for two. Yes.
Like in the cortex, a lot of this plasticity modulated ideas are those waves not present in the cerebellum, or
actually, that's a good question. I don't know the answer. I'm not too sure. That's a good question. I have no idea. Yeah, it's a bit maybe a neurocentric view, but I don't think there is lots of. I don't know. Okay, so maybe one thing you can say with respect to the cortex is actually many of the rules in the cerebellum are inverted with respect to cortex. You have depression instead of potentiation, etc. Okay, so let's do. Okay, so sorry. So I wanted to show you a recent. So this, the fact that there is depression by joint olive and brain stem stimulation goes back a long time ago, and also this was a pioneering experiment. It was in Japan, and they have been redone many times in the course of years. So here, this is an experiment in the lab of Jennifer Raymond in the context of this ideal conditioning where you have specific requirement. And what you see here is that, okay, if you have depression, so let's say here that you, no, here actually it's, sorry, it's a slice word. So either you pair fiber with tiny fiber signal at the same time, and when depending on the region of the cerebellum, you see different things, but in the flocculus, which is the region which you control the movement of the eye, at least here you don't have depression. And so this is quantified here. So if you do it at 120 milliseconds, you get the large depression of this parallel fiber Purkinje synapse. And in fact, this timing between the parallel fiber, so here you have so this is cipher, so you have input in the parallel fiber, and then you stimulate the tiny fiber, so you can do that at different times. So at 120 milliseconds you have a large depression, but if you do it at other time interval, you see that, okay, you have a very specific depression at 120 milliseconds. So this is a really match, so its depression is matched to sensory. And so this delay is actually the delay that we could compute from visual feedback. So visual feedback is quite slow. So when you have something in the visual field to reach, this information to reach the cerebellum, it would take around 120 milliseconds. So the idea is that here what you have is some plasticity rule that is really tied to the biological feedback deal. Okay, and so here I show you this classical depression by combining parallel fiber information with tiny fiber signal. So here again, at 140 milliseconds, the idea is that if you have this, the tiny fiber is signaling an error to the Purkinje cell, and that is inducing plasticity. The experiment was with other groups showing that, okay, if you put, of course, if you have only depression at the end, all the synapses would have vanished. So you need some compensating kind of potentiation. And other groups have shown that if you do parallel fiber alone, then you get potentiation. And the idea of this thing is, as I was saying, is that the thing is inverted with respect to cerebral cortex, that you have two thresholds of calcium, and if you have so at the synapse, if you go above the first threshold, you potentiate, and about the second threshold, when you have this large stimulation by the tiny fiber, you press. All those of you know a bit about plasticity and synapse. Okay. Okay, so actually, when should it end? So we should end at 1.
Since you start late, can probably go extra 10, 15 minutes as you see fit.
I don't want everybody to miss the pizza. And probably more attractive. Okay, so there is the cerebellum. There are these theoretical ideas, and I'd just like to discuss a little bit how they have evolved and what people are doing. Okay, so this is a bit more theoretical. So again, as we saw in Nitya's talk, the idea is, okay, what is this high-dimensional representation? The idea is, okay, the first representation where I have so if I have a representation with n neuron, I can take this as a point in an n-dimensional space. So I would say that I have a representation of this activity in a space of n dimension. So it could be with rate, or if I take a spiking neuron and short time beams, I can, I have a representation with plus or minus 1 or 1 and 0, saying that, okay, I have a spike or not a spike in this time beam, and plot this in a high dimensional space, in a dimensional space. In space of size n. Okay. So Mark. Oops. Can I put it somewhere? Rama, you have an adapter.
For what?
For the plug.
No.
Sure. Very good. Thanks. Thank you very much. Okay, so what is my reason? So the idea was first proposed by David Mars. So he says, okay, if you go into a high-dimensional space, in some sense, this will reduce the overlap between inputs. So input that have some overlap in the input layer, if you go to a high-dimensional space, then they will tend to be orthogonal. So what's the reasoning? So he said, reasoning is quite simple. He says, okay, let's take two sets here of fiber, which are active and which have an overlap W. So I have two sets and they overlap by W. So now if I map this to a new set of cells, and each one is connected to K fiber and require K input to find. So this is a supposition. Okay, I map it to a new set of cells, a little bit like this new cell, that are taking K input from this active fiber. So okay, so now if I look at the different possible representation of L fiber by these cells, okay, it would be to draw K fiber among L, so each shell can draw K fiber. So the number of possibilities is this. But the possibilities for the overlap in this new representation is not W. Is again, you should choose K from the W that are common for the overlap. Okay? And so if you look at this overlap between these two representations, you have this W over K about this total number of possibilities. So the overlap in this other representation, where each shell is K, is W over L over K, and quickly tends to 0 here, to 0 as increase. So the thing, so if this is smaller than 1, that would be much smaller. Okay, so the idea is that you orthogonize tokens. So this has been taken up in a more recent paper that I showed it in Kumar and Larry Abbott. And again, they consider this setting where you have a mixed layer neuron, okay, would be the random set here, and we can forget about this. Because they look at this in other settings, like the mushroom body of the lower. I won't discuss this here. And then you have this thing that are taking K into structure. Okay, so now you can try to compute so suppose this is completely linear. First of all, if you want to compute the dimension of this activity, so one way to quantify this is to measure, as Nikia was saying, the correlation of activity in this layer. So you just take say for example, firing rate of these two neurons, you compute the correlation between that. This will give you a matrix of correlation. And then one way to compute the dimension of activity in this layer is just to do to diagonalize this. So go to principal component. You see this activity. Okay, it could be either a ball or very elongated. So you compute the different moment of this activity by diagonalizing this matrix of correlation, and then okay, you can have one measure of dimensionality is this participation ratio. So if all the eigenvalues are the same, then here you get m squared over n. So this is n. So it says that okay, the dimension is basically the dimension of space. You have a ball is the dimension of space. But say if it's very elongated, so suppose the one eigenvalue is much bigger than the other one, so it dominates these two sums. So you have basically this lambda 1 square over lambda 1 square gives 1. So this thing in some sense interpolate between, as it's sketched here, between something where the three-dimensional space is free if the activity is entire spherical in some sense, and if there are preferred direction, it will tend to measure the activity in this preferred direction. So it will give a sense in which this activity is going into space. So now you can look at the case of linear transmission. So you have here the sensory input. Each one is X is just a linear combination of this input, and since it's a linear thing, and here they take in the simplest calculation you can take synapses that are all the same way. You can compute that, and what you find actually is that the dimension of activity in this layer is not bigger than the dimension here. You have the dimension itself is exactly the same. It's even lower than the dimension in the first layer. So that's what is shown here. And if you put a very large expansion ratio, you can get basically. And so if you have nonlinear transmissions, you can go a bit, you can look at the paper, you can do a bit better, but it's still linear in length. So you can have, you gain some dimensionality, but it's still proportional to the dimensions of the. And then if you optimize, I forget to put a nice graph here. So that is, okay, so you see that here it saturates. And so their idea was, okay, but maybe they wanted to have a sense in which you remember that for the brain cell, this K is quite small, okay? So if you look at that big man says, okay, K is quite small, even K small is useful to orthogonize input, so it's economic not to go to higher K. And they wanted to formalize that. So instead of just doing that, they would optimize what you get as a dimension with some resource constraint, and the resource constraint they choose is just the total number of synapses. And if you do that, there is a graph that I didn't show here as a function of K, you get something that peaks around K equals 4. So the idea again is that, okay, if you have a certain number of synapses that you have to put in this layer, the best basically is to have 4 synapses. But of course, I mean, here you optimize for the number of synapses. You can choose n as you like. So in some sense, maybe this is correct. But, n, in some sense, producing more neurons is also very costly. So I'm not completely sure. But in any case, that's it. Okay, so now the question is, can we see this high-dimensional activity in animals, real behaving cortex? So this, okay, so you hear me still? Okay, so this has been a bit controversial. People have tried to measure the dimension of activity in, say, parallel fibers. So what, basically is the activity of this granule cell layer. And so so here I show you a paper from Angus Silver group at Cambridge. And so the idea is that, so before this there were other papers who were saying, okay, actually we looked at the dimension of activity in this parallel fiber layer, and we find a low dimension. And the idea is that, their idea is that, okay, they found in this previous study, low dimension were found because the behavior was very limited. So sometimes the input to the granule cell were also very low dimensional. So they tried to measure this with higher input. So they have a mouse on a wheel that can do, I mean, it's head fixed, but it can run, do things. So the behavior is a bit complex. And so they looked, so they measure by calcium the activity, so you have the granulosity on this parallel fiber, so they monitor that. So that's here for you. This is a kind of image they show, so you have these activities on parallel fiber that are localized. So some of them are very correlated, so the idea is that, okay, they are on the same parallel fibers, and you have others that are different, so you can see that if you do correlation, you have things that are very correlated in this granularity. And so now you can look at this activity. You can look at this activity. The first thing you see, or they see, is that there are actually two clusters. And so one is simply because the mouse has two states. It can be active, running and whisking, or simply being quiet on its wheel, and it alternates between these two behaviors. So that's what you see here. Here it's a measure of it is what is called whisker set points. I think when mice are running, they put their whisker forward. So if you have the mean whisker position, you can track this thing. And the first component of this activity in parallel fiber is just reflecting this quite accurately. So you can discriminate these two states accurately. But now you can go a bit further. And so, first of all, you can ask how many Purkinje cells are needed to reconstruct behavioral variable accurately. So if you do that, and you try to see what is the variance explained with the number of PC, you see that, okay, for, say, reconstructing whisker set point, this activity, the best parallel fiber would still have 40% unexplained variance, and you can increase this with 10, and even better with 100 PC. So this is this kind of curve and the variance to explain. So to explain what behavioral variable, you need a lot of PC. You can do that also for locomotion speed. And then you can try to see what is the activity in this set of recorded PC. So they try to do that by some kind of sophisticated PC analysis, that is some kind of validation. So here, what so is that for different mouse, they have different results actually. So different colors here are different mouse. And so you see that, okay, if you increase the number of components, you increase the variance explained up to a point where in some sense you are overfitting, and then it's not good to increase the number of components. And so basically you can okay, so they put all these mouse data. I mean, there are 3 mouse that here. So they try to extend. So if they extrapolate, if you want to extend all the variants, you would have to have 61 dimensions. So basically, this is and they are looking at the correlation. They have about 300 axons. So it means that, okay, for each dimension, you have, for 5 neurons, you have 1 dimension. So we conclude that, okay, this is actually very high dimension. Basically, for each 5 brain cell, you have 1 more dimension. So you are, this data can say that, yes, the brain cell layer goes into dimension, high dimension. Okay, so sure. Okay, I can try to explain the next idea that was developed. Is the idea that Purkinje cells, so this Purkinje cell receive a lot of input. So an idea that was proposed very early again by David Marr and James Adams is that they are acting as perceptron. So this is again very similar to Nitya's code in some sense. So I remind you what perceptrons are for those who don't know. So it's just in some sense the simplest learning machine that was introduced very early AI field. So you just have inputs, you do the linear combination of these inputs, as Mitya was doing this morning, but you do slightly more, you put a threshold, and you output, if you have, say, a binary, something that is active or not, you put a threshold, the function here, excite function, so if the activity is above the threshold, it would be a 1, if it's below threshold, it is 0, or you can put the sign in machine learning, plus or minus 1, depending on the threshold. Okay, so this is the classical learning device. And basically the simplest task is a classification task. You give some inputs here, and you want to associate it to some output. And so the way you have each input has is n dimension, and what you want to do is say, put here image, and say if there is an animal in this image or not. So this would be one image. If there is an animal, it's 1. If there are no animals, it's 0. So that's the simplest classification. So as Mitya was showing this morning, basically what you have to do is the task is trying, if this is a discrimination task, what you like to do with this machine is trying to discriminate, so here I put it in 2 dimensions, you have points that, so this is the input in 2 dimensions, so they are set of points, so 1, 2 here, and what you like to do is to find some plane that separates these 2 things into 2 categories. Okay, so this would work on this task here. You can put the linear thing and separate the blue from the red. But if you have this pattern, it's not possible to put a single line where all the red are on one side and all the other are on the other side. Okay. So one contribution was this Minsky and Papert contribution that pointed out that if you have this kind of thing, you cannot learn it by the perceptron. So basically their conclusion was that the perceptron was turned out not to be correct given the actual development in machine learning. Okay, so there are 2 early things that were done with this perceptron. I'm just reminding you that before going to the future. So one was this very early thing by on the perceptron algorithm by Rosenblatt, who invented this algorithm, which showed that it's always, if there is a solution, it's always possible to find it. That's this perceptron. And then the question is, can we measure the perceptron's maximum capacities? Is how many associations such a machine can learn. So just to remind you, so basically what you do is again learning. So it means that, okay, you look at the example that you have. If the plate that you have at this time gives you the correct output, you don't do anything. And if the output is wrong, you modify the weight so as to get, so this is the output, so you modify the weight so as to go in the right direction. So you depress or increase the weight. And so the key result of Barn that with this procedure you find if a solution exists, you find it in finite time. Because each time you basically you do this procedure, you go closer, this vector go closer to this one by a finite amount. So that's a nice result. And the other one that was the only thing that I'm showing you is if you have two if you have 2 points, of course you have two key different ways to color them. Each one you can color red or blue. And so the question is, if these points happen to be in n dimension, how many of this coloring can be separated by an interplane? So if you have the simplest setting where, say, you take this, so you can take this point at random, but you say the output, you randomly associate the point and the output is plus or minus 1. And with equal probability of the 1 and the minus 1, then the solution to this number of coloring was given by Cover a long time ago by a combinatorial argument. So you can write exactly what it is. And then, so what you find is that basically the number of associations, so here you have the number of coloring that are separable over the total number. So if P is smaller than n, actually all the coloring are separable. So that you can exactly do this linear separation, always. And then if you increase P to 2P, then most of them are colorable in the sense that if n increase and P over n is fixed, this will go to 1, so which is this different curve here. So the result says that basically in high dimension you can store 2n associations. So you have 2n input, output that you can choose arbitrarily that you will be able to separate. So again, this says that it's good to go to high dimension because n is the dimension of the input to the self-perceptron. So the higher you go with n, the more association you can store. So that's what old argument by Andrews to say, okay, why do we have this granular layer? Because actually we go with the granular set to this high dimension and we can store many associations, many more than the granular set. There were a lower number of friends. Okay. So I showed you a very sketchy perceptron, but we can try to do a bit better. And so again, we can look at the parallel fiber and the complication. So let's say it's the perceptron. So we have weight here, but there are things that we can impose. First of all, we know that this weight are not different sign. We know that these granular cells are excitatory cells, so all these synapses are positive. And we can also, we know that, we want to have, we know that there is this Golgi cell, so that this granular cell layer, there are not so many of them are active, so we want to see if we can put a coding fraction here, so that the input, for example, are random, but with a specified fraction of 1 and 0. And maybe also we want the output to have some coding level. So in this setting, the estimating the number association is more complicated. So okay, so we can use this setting. So there are techniques that have been developed to analyze this setting. But you can wonder if it's worth to do that, because actually experimentally it's very difficult to measure the capacity of the Purkinje cell, how many associations the Purkinje cell will store is very difficult. So one thing that has been done is to try and see if we can get at this information in a different way. And so Boris Barbo has this idea that maybe one way that would be interesting is to measure the weight of the parallel fiber Purkinje cell synapse. So before the pizza, I just show you that. So this is slides were doing, so this is slide one, so this is the Purkinje cell, the parallel fiber, so you can stimulate the granule cell and measure the response in the Purkinje cell. And what you, so this is sketched here, you have this, so this is a batch count. So you stimulate the granule cell and you measure the response in the Purkinje cell to the amount of depolarization induced by this synapse. So it's a proxy for synaptic strength, and you can measure the histogram of what you have. So this is what you have. But there is something that does not appear on this histogram, so that they measure a lot, actually, about 600 of these contacts, and so they found about 30 that were measured, but most of them didn't give any signal. So you do that, but here you don't detect anything. So you could say, okay, there is simply no synapse. But you know that with the anatomy here, people have looked, and what they estimate is that when the granule cell traverses the Purkinje cell, there is a probability of 50% that it makes a real synapse if you do electron microscopy. So in fact, here there is a puzzle, is why you detect so few synapses? And the question is, why are there so many silent synapses? Why are there so many useless synapses? So this, so if you think that, okay, maybe there is some truth in this perceptron idea, you can try to estimate this number of, at least the distribution of synaptic weight from the perceptron. So this is a bit more involved calculation than the cover techniques. You have to use techniques from StatMech that have been developed along the year. In particular, by Giorgio Parisi, who got the Nobel Prize 2 years ago. And they are now have been made rigorous by many mathematicians, including Talleyrand, who got the Nobel Prize this year. So there is a whole body of this thing. The crucial idea for the perceptron capacity was put forward by Elizabeth Gardner long time ago. The idea is, okay, is to compute, so you have all these possible synaptic weights, so that's a space of synaptic weight, and now if you have association, it gives you constraints. So the idea is to compute the volume in synaptic space that is compatible with the constraint. And of course, if the volume is zero, it means that there is no solution. If the volume is finite, you have a number of solutions. And so what you can do is to apply these techniques with positive weight threshold for the Purkinje cell without diffraction. And you can say robustness parameter, meaning that you are not only above threshold when you are positive, but above with a certain, away from threshold with the parameter.
Vincent, maybe we can wrap up here?
Yeah, I'll wrap up. Yeah, I show you this and I conclude. So, okay, you can compute this distribution of synaptic weight. That's what I'm showing you here. And in fact, if you learn as much as you can in this perceptron calculation, what you find is that there is a large proportion of synapses that have zero weight. So this is a purely mathematical calculation, and here you have the number of silent synapses as a function of this parameter. We just measure this robustness parameter as a function of the fluctuation in the input, the activity of the input. And so, even if there is no robustness at all, you have 50% silent synapse, and then if you increase the robustness, much more synapse. And if you compare with the experimental data, what you find, you can find the best fitting parameter. So you find this robustness parameter, the mean synaptic weight, etc. And you find that, okay, if you say that there are 80% silent synapse, you find, first of all, that there is the input are very sparse, and you fit this histogram. So what I just, before concluding, sorry. So these histograms are very simple. They are just Gaussian and truncated. And so the question now is, why do we get zero weight, synapse with zero weight? It's just a very simple thing that when you do this on the computer, you try to optimize this association. You increase or decrease the weight of synapse, but you cannot decrease below zero. So you have a number, the more you put constraint, the more synapse accumulate at the bound. Okay? So here you have a Gaussian, and all the synapses that would have been negative are just accumulated here. Okay? So that's the result of the calculation, which says, okay, you have a lot of zero synapses just because it's a process of learning with a bound at zero. So in some sense, this view of the perceptron at least gives a potential explanation why you see this experimental result that you have a lot of synapses at zero weight. Okay, so I conclude here. So it just try to show you two main results. I mean, this field is going into high dimension seems to be true for this random cell, and the fact that the protein can act as a perceptron seems at least compatible with some data that people have. So I wanted to say a little bit more about the time basis and the function of the cerebellum.
So any questions? Emerging questions from the lectures? Yeah, there's a question there.
I'm going to be quick here. So a little bit beyond the scope of this talk, there's like the air signal from the common fiber from the interior. Beyond the scope of the talk, I was curious about the air signal from the interior olive, and what's known about how it's computed. Maybe question one, and briefly, whether or not that signal is even there to begin with. It seems like the literature, from my reading, has kind of surprisingly failed to find a robust air signal in the interior olive.
Okay, so that's a very good question, because this would be the topic of lecture 2. So the question that was raised is very good. Is in all this theory, you think that suppose that the olive has the error signal, but the question is, how does the olive know what is the right error signal? If you have a complex movement, you have a very low information that is given to you. I mean, the thing you learn to cycle, you just know if you fall or not fall. And you have many muscles that you should adjust. So how is the olive knowing exactly from the fact that you are falling that you should adjust all these muscles? So that's a very good question. I try to discuss it in the next lecture with also this question, what is, if you recall from the what you see.
But do you believe that the cerebellum is actually doing classifications?
So, okay, so that's what the part of the talk.
In terms of the
so no, the
experiment,
cerebellum is what we not doing classification. This is but at each moment, here you should see that, okay, I receive a signal, do I emit a spike or not? So this is what the cerebellum is doing. So in some sense, it's a classification in time. You receive some input from your sensory signal by your should the Purkinje cell which receive the signal emit a function potential or not? So if you think of this as a time slice, at each time slice, you should know if you emit an action potential or not. And actually, going back to what the other cells are doing, if you stimulate a parallel fiber, you induce a spike for the Purkinje cell, but then you have all these inhibitory interneurons that look like feed-forward inhibition, so after that you really stop the activation, so you have feed-forward inhibition. And so sometimes you really emitting spike, looking at pattern after pattern that are coming from the parallel fiber. That's the idea. Maybe we discuss in front of the pizza.
Yeah. Okay. So we have pizza in the which floor?
This floor and 7.
This floor and 7. Yeah.